have you ever had this really complex idea in your head? Maybe a new gadget, a piece of furniture, a part for a car, and you thought, how on earth do I explain this to someone so they can build it exactly right? I mean, perfectly, down to the last millimeter? Well, that whole journey, from an idea in your mind to a real, physical thing you can hold, that's one of the biggest challenges in making anything.
So yeah, how do you do it? How do you describe a complex, three-dimensional shape with absolute precision so there's zero room for mistakes or, someone's personal interpretation? Because if you just try to use words, the gap between what you're picturing and what you get can be, well, huge. I mean, imagine walking up to a machinist and saying, "Hey, I need a boxy thing with a hole in it." That's basically useless, right? But if you hand them a technical drawing, that's a whole different story. That's not a suggestion. It's a contract. It is a precise, unambiguous set of instructions. It makes sure that what gets built is a perfect match for the original vision. And that right there is the whole point of engineering drawing. Okay, so here's the plan. We're going to start with that core design problem. Then we'll dive into the amazing language that was invented to solve it. We'll see how AutoCAD brought that language into the digital age. We'll peek inside its virtual toolbox, build something in 3D, and then tie it all back to the world we live in. Let's get into it. So first up, let's really dig into this problem. How do you get an idea out of your head and into a machine with absolutely no errors, no information lost along the way? Well, the solution, which was developed over hundreds of years, wasn't a piece of software. It was a language, a visual language, with its own grammar and its own rules that anyone, anywhere in the world, could learn to read and understand. And the cornerstone of this language, the big idea at the heart of it all, is something called orthographic projection. It sounds complicated, but it's really a clever, standardized way to show a 3D object on a flat 2D piece of paper. You basically project different views of the object, like what it looks like from the front, the top, and the side onto these imaginary flat planes. And this image right here makes it all click. See the 3D cone? If you look at it straight from the front, the shape it projects is a triangle. But if you look down on it from the top, it projects a perfect circle. By capturing these different views, kind of like taking perfect flat shadow pictures, we can fully define the 3D shape.
And here's what that looks like in practice. You get two simple, flat drawings. The top view shows a hexagon and the front view shows a rectangle. Now, either one of these by itself isn't enough information, right? But put them together and they describe that 3D hexagonal shape with total clarity. No guesswork.
Now, every good language has grammar, and this one is no different. It comes in the form of different types of lines. A thick, solid line, that's an edge you can see. A thin, solid line is usually for showing dimensions. And a dashed line, that's for a feature that's hidden from your current view, like the inside of a hole. Every single line has a very specific job.
And the vocabulary, the actual words of this language, are the dimensions. These numbers are the absolute non-negotiable truth. They tell you the exact size, the exact location, the exact geometry of every feature. They completely eliminate the need for anyone to ever guess or assume anything. For a long, long time, all of this was done by hand. I'm talking drafting boards, pencils, rulers, painstaking work. But then, of course, computers came along and changed the game. The language itself didn't change, but the tool we used to speak it became unbelievably powerful.
And really, the best way to think about it is that AutoCAD became the ultimate word processor for the language of design. It didn't invent the grammar or the vocabulary, but it perfected the act of writing it down. It made the process incredibly fast, unbelievably precise, and super easy to edit.
Okay, so let's pop the hood on this digital toolbox and take a quick look at the essential commands that actually bring these designs to life.
All right. Probably the single most important concept for staying organized in AutoCAD is layers. Just think of them like a stack of clear, transparent sheets. You can draw all your structural walls on one layer, put all the electrical wiring on another, and all the plumbing on a third. This lets you manage these incredibly complex drawings by just turning different layers on and off whenever you need to. It's a lifesaver. And hey, don't just take my word for it. As one pro CAD user on Reddit said, good layer management is absolutely, fundamentally critical. It's really the difference between a project that runs smoothly and one that's just a complete chaotic mess.
So, the basic building blocks are what you could call the creator's kit. With just a handful of these commands, like line for straight bits, circle for, well, circles, arc for curves, and spline for those really complex organic curves, you can pretty much draw any 2D shape you can think of.
But the real power, the real magic, comes from the modifiers kit. These are the tools that let you edit. Commands like trim to snip away extra lines, fillet to make nice rounded corners, extend to stretch a line perfectly to meet another one, and offset to create a perfect parallel copy. This is how you turn rough ideas into precisely finished parts.
Now, 2D is the foundation, but the part that's really amazing is how AutoCAD uses those same exact principles to build full-blown three-dimensional models that you can spin around and look at from any angle.
And the process for doing it is so simple and logical, it's beautiful. Step 1, you draw a flat 2D shape. We call it a profile. Could be a circle, a square, anything. Step 2, you apply a 3D command to it, like telling it to extrude or pull that shape upwards. And step 3, boom, you've got a 3D solid object.
And here it is in action. Look, on the left, you start with that simple, totally flat 2D hexagon. Then you hit it with that extrude command, giving it some height. And just like that, on the right, you have a solid 3D object. It's an incredibly powerful and intuitive way to build.
And of course, that's just the beginning. You get into more advanced tools like Revolve, where you can spin a 2D shape around an axis to create things like a wheel or a bowl. Or you can sweep a shape along a path to make things like pipes or springs. The possibilities just become almost endless.
So at the end of the day, it's this combination, a universal visual language supercharged by a digital tool that is the foundation for almost all modern design, manufacturing, and construction.
And this right here shows you the incredible scale of what's possible. We're not just talking about little machine parts. This is a massive, complex site plan for an entire neighborhood. Every single road, every property line, every utility pipe is defined with absolute perfect precision, all using those same core principles we just talked about.
You know, from the smartphone in your pocket to the chair you're sitting in, to the building you're in right now, this universal language of design has quite literally built our modern world. It's this amazing system that allows a single, precise idea to become real anywhere on the planet. The only real question left is, what are we going to build with it next?